Hi there, my name is Wojciech Pruszkowski, and I'm an application engineer working for SOFiSTiK. Today, I would like to welcome you to this short SOFiSTiK webinar on the human-induced vibrations on the footbridges. So, this webinar aims to briefly define the problem along with its basic underlying theory and present the solutions possible within the SOFiSTiK software. So in terms of the agenda for this webinar, we will start off with a problem statement and description what is to be understood by the terms resonance and excessive vibration. We will then discuss the primary design criterion that is the human response to vibration. We will review the mitigation methods available if the design exceeds either ultimate or serviceability criteria, which will conclude the general part of the webinar. We will then review the varying types of loading induced by the pedestrians on the footbridge, and we will present their analytical representation, which is obviously necessary if we plan to recreate those loadings in the FE system. And once all the required theory is assembled, we will present and discuss three examples. Example number one, which represents a stationary loading on a straight geometry calculated with the ASE module. Example number two, which is a moving load on a straight geometry also with ASE module. And example number three, which is a moving load along a curved geometry done with a dyna module. Footbridges may often be modeled as equivalent single degree of freedom systems. A SDOF model represents all components in the differential equation of motion, and these are a mass, a viscous damping coefficient, a stiffness coefficient, and the resulting displacement x over time. Those models can be extended further beyond just a free vibration to include external effects also. For instance, on the system on the right, we have a base motion that can approximate an earthquake or the impact of external vibrations on foundations in general. Or, as it is more interesting to us on the left, we have an SDOF with a external forcing function acting on the system. We have several classes of forcing, starting with impulsive excitation, which represents impact loading. We have then a harmonic excitation, which can be caused in a number of ways, for example, as a result of out of balance rotating machinery. But for our application, it can also represent Vandal loading. We have a periodic excitation, which is any excitation which is periodic over a time interval t. That is usually described by a Fourier series, and for our application is very useful to describe human walking, running, or jumping. We also have transient excitations, which is, for instance, a car passing by, and we have a stochastic or random excitation, which is a wind or waves. So what is to be understood when we're talking about the resonance? A resonance occurs when a natural frequency of the structure matches forcing frequency of the external loading or its multiple, as handsomely presented in the graphic in the bottom of the screen. This is an inherently dangerous scenario which can lead to excessive vibrations felt by the user at the minimum that can breach serviceability limit states, or it can lead to structural collapse at the maximum, which is an obvious ultimate limit state failure. Multiple factors decide whether the resonance is an SLS annoyance or an actual ULS danger. These include not only external force characteristics like frequency and magnitude, but also structural characteristics of the system itself, like its mass and stiffness and material and its damping properties. So the best known case of the resonance going horribly wrong is a galloping Gertie, a classic case of Tacoma Narrows Bridge that collapsed in 1940s due to vortex shedding that is being displayed in the university halls all throughout the world, really. This is a case that really kicked off the whole investigation of aeroelastic effects, and many lessons has been drawn from this example, especially about cross-section optimization for the bridges exposed to high winds. As discussed, the resonance amplitude and thus resulting strains depend on multiple factors and really rarely lead to structural failure and collapse. On the other hand, they can very easily lead to excessive vibration, as it happened in these two highly publicized cases. The economics of modern design and construction dictates that the structural design is to be as efficient in terms of material volume as possible. This has increasingly led to slender and flexible structures with certain liveliness and vibration. The Millennium Bridge in London has been recorded to vibrate in the lateral direction on its opening day due to the unforeseen pedestrian excitation, and Human Bridge has been seen to sway vertically under heavy wind loading some 23 years after its opening. Both led to temporary closure and follow-on investigations. These do not lead to structural failure, not even close in fact. The stresses and strains involved in these motions often being 10 to 100 times less than those which might initiate any structural damage. Both examples had no damage to report after the incidents either, after the investigations concluded. Nevertheless, Millennium Bridge has received vibration dampness and was tested by Arab in its family members anecdotally, while Human Bridge was left as is. So the excessive vibration is not dangerous, yet it is still unacceptable. The question remains why, and the answer is very simple, and that is the limit of comfort within the human response. In order to evaluate the impact of oscillation on people, an appropriate parameter should be selected. This parameter highly depends on the frequency range the analyzed structure operates in. And so, in the frequency range of 1 to 10 Hz, the perception of oscillation is proportional to acceleration, while in the range of 10 to 100 Hz, it is proportional to velocity. There is no such thing, however, as a human fixed perception threshold. A comfort level and vibration acceptance level is a highly individual matter for every person and depends on the myriad of factors like age, gender, occupation, or even the situation that the person finds himself or herself in. For example, a different level of comfort in terms of vibration can be expected when the person is driving a car in comparison to the situation when the person is in their own bed sleeping. Having said that, there are indicative threshold values available to serve as design criteria for structural engineers in the design standards with BS 5400 or ISO 10137, to name a few. It is always advisable, however, to check and follow the local applicable standards first. And so the significant exceedance of these threshold values may result in user discomfort and even fear and reluctance to use the structure, just because the insignificant utilization ratio has been reached does not mean that the deformation and vibration of the structure is not off-putting. So it is therefore a serious matter for the designers to consider. To conclude the general introduction part, let's get slightly ahead and consider the possible excessive vibration mitigation methods. If the structural analysis at the design stage or user feedback post-construction, so not preferred, indicates vibration issues, then multiple design choices are available to remedy it. First of all, let's have a look at tuning and stiffening. All means possible should be taken to avoid a fundamental frequency of the structure in the range of 1.6 to 2.4 Hz, and to a lesser extent the higher degree of 3.5 to 4.5 Hz. These frequency ranges include the most common frequencies associated with human motion. Retrofitting the bridge structure with additional members can be a prohibitively expensive procedure, so addressing all potential issues at the design and analytical stage is obviously the preferred option. There are also external systems that can be incorporated within the structural system, either at the design stage or as a retrofit to aid the vibration control, like viscous dampers. The external dampers can be incorporated in bearings and supports or as a thick layer of high viscosity asphalt for the bridge surfacing. External dampers were retrofitted to the Millennium Bridge in London, as shown in the photo, which solved the lateral sway vibration problems entirely. Another option are tuned vibration absorbers, which are a subsidiary mass spring damper systems whose natural frequency is nearly the same as that of the bridge itself, but with a small fraction of its mass. The tuned vibration absorbers, if executed properly, are a very cost-efficient and effective solution with a minimal footprint within the structure. And with that, let's wrap up the theoretical considerations and let's have a closer look into the practicalities of the task, that is analyzing the response of the footbridge under pedestrian traffic. So there are three main components needed for this analysis in SOFiSTiK. Number one, we need to define a complete FE system, together with its geometry and material data, dead and superimposed dead loading, natural frequencies, and structural damping properties of the materials and external systems. Number two, we need to define forcing functions together with their magnitude, frequency, and their route along the bridge if the load is not stationary. And number three, we need to define the time history analysis of the system under the given loading. A timestep size is critical as it needs to provide enough fidelity into the forcing function acting on the structure without overloading the analysis with an unnecessary amount of steps. And engineering judgment applies here with a little bit of experience really. So it is fair to say that the system and the time history components of the analysis are well defined. It is not the case, however, with the forcing functions, as the main issue with this type of dynamic analysis lies exactly here, in understanding and defining the loading that is meant to represent the pedestrian traffic within the FE system. The main problem with pedestrian loading is its unpredictability and complexity in the number of possible scenarios. This is why a vast number of footbridge designs has been executed using the rule of thumb approach in tuning the structure's natural frequencies and static response, rather than studying the structure under the actual dynamic loading. This approach allows for the engineers to simply go around the problem of defining the said loading with usually good enough effects. As discussed earlier though, the financial and environmental realities of the modern civil engineering practice usually place a strong emphasis on the efficiency of designs and reducing the material volume. This in turn results in more slender designs and thus increases their vibration susceptibility. This means that the ability to study the dynamic response of the footbridge accurately is more important than ever. And that process starts with the ability to represent the loading conditions in a form of mathematical formulas that can be incorporated into the FE analysis. So let's have a look first into what can we expect in the average loading scenarios from the pedestrians. Various design codes provide some insight into the typical design cases to incorporate, and I was pleasantly surprised to find a short clip showcasing some of them. Let's start with the loading representing a standard, single human body motion of various types, either mobile or stationary. A standard design case usually to be considered is a human motion of 2 to 3 pedestrians walking or running in step at the fundamental frequency of the bridge. Additional investigation can also be required for cases where a stationary group of people jumps in step. The loading of other types, where a repetitive feeds impact on the bridge's deck is not considered, can also be required by the footbridge design scope. These types of forcing can include, for instance, an intentional excitation by small groups of people trying to swing the bridge as an act of vandalism. All the loading scenarios mentioned so far assume a single pedestrian or a small and easily definable group. What is also required is a way to represent a large number of independent pedestrians without any particular synchronization, or a so-called pedestrian stream, as represented by a still picture in the bottom right corner. The loading conditions presented are just examples and are in no way an exhaustive list. You should always adjust your loading to the design brief, follow the engineering judgment and experience, and be informed about the required loading scenarios by local codes and standards. In the previous slide, we have summarized some typical human body movement across the footbridge for a single pedestrian. Let's have a look now at the practical means of representing these movements as forcing functions acting on a FE system. In general, the time domain models are the most common models for walking and running. They are based on the assumption that both human feet produce exactly the same force and that force is exactly the same with every movement cycle. Hence, the resulting force is periodic and can be represented by a Fourier series. The Fourier coefficients and phase angles for various human activities have been ascertained in experimental research. The table on the right side lists some coefficients and phase angles as proposed by several authors. Please refer to the JRC report mentioned and the relevant literature if you wish to learn more. The plot on the bottom left side is showcasing a vertical loading over time, obtained using the Bachmann coefficients and associated with one pedestrian walking. A time domain function like this is an input ready to be used directly in SOFiSTiK. When it comes to intentional excitation, the mathematical description of the loading function depends on the nature of forcing. In the scenario where a group is trying to sway in the frequency of the bridge, there is a constant feet contact with the deck with no impact observed. Therefore, a sine or cosine function can be implemented. When the group is trying to jump in tune, which is much harder to execute than swaying in tune, by the way, we come back to the Fourier series as described in the previous slide. A repetitive impact, or any other scenario for that matter, can also be introduced into the model as a discrete polygonal function that can be defined by hand, by spreadsheets, or by using parametrics. Several data pairs are required, with each pair describing the numerical value at the specific time point. SOFiSTiK is able to interpolate linearly between those time points to create any loading function. All the previous considerations presented so far account for dynamic effects induced on a detail level, and might not be practical to simulate the impact of a daily random traffic or larger groups that could be expected on the bridge's opening day, for example. The French CETRA Association has proposed a loading model that has become widely adopted since. The model, upon calibrating it to the specific application via a set of parameters like step frequency or the expected traffic density, allows for describing the idealized pedestrian stream consisting of a specific number of perfectly synchronized pedestrians. The loading model is then applied to the bridge geometry according to the relevant mode shape. We are barely scratching the surface here in terms of general knowledge, obviously. If you wish to learn more, then please refer to the relevant literature. The three titles presented provide an excellent starter pack and a wealth of practical guidelines in the subject of human-induced vibrations on footbridges. And so, we are finally arriving to the matter of actual SOFiSTiK modeling and analysis. We will consider three examples. Example number 1, consisting of a simple straight geometry with concrete slab and 11, 14, and again 11 meter spans. Here, we will consider stationary loading models only. Example number 2, with the geometry identical to that of example 1, but with loading moving along the bridge axis. And example number 3, with the curved geometry and the loading model moving along the bridge axis again. So let's jump into the first example. This slide contains all steps required for us to perform the analysis. Defining material and geometry data, DL and SDL loading relevant for natural frequencies of the structure, investigating natural frequencies and associated model shapes, defining the Rayleigh damping for the relevant frequency range, assembling the forcing functions, and performing the time history analysis. So let's switch over to the SSD now and go through these steps. You can always refer to the slide in the video for the short description of every step. Once the example file is opened, you will notice on the left three task groups, one for each example. We will start off with example number 1. There are several TEDdy tasks here, each for every design step as discussed in the previous slide. We will start off with material and system generation. This task just serves the purpose of introducing the concrete and geometry into our system, and is frankly of the least importance to our workflow and can be replaced by any preprocessor of your choosing. Next up, we have deadload and superimposed deadload generation. We create one load case for each, so load case 1 for deadload and load case 10 for superimposed deadload. We then execute load case 10. It is required for natural frequency analysis. We can only use those load cases that has been already calculated to generated nodal masses from them. And then we create load combination of LC1 and LC10, and this load combination will be used down the line as a primary load case for time history analysis. Let's look at determining the natural frequencies of the system next. For that purpose, I can use the graphic interface called eigenvalues. And I'm fine with first 6 eigenfrequencies, starting from the load case number 6001. I do have to remember about additional masses. I want to activate load case number 10, so my superimposed dead load in the direction z with mass acting in all directions. Let's execute. And let's review the results that we got. So right off the bat, I can tell that I have at least 2 relevant natural frequencies. Relevant in the sense that they approach the frequency of either human walking or human running, which may cause resonance. So I will want to investigate it further. I will also want to use these 2 natural frequencies as my relevance frequency range for Rayleigh damping. Let's have a look into that task now. So in the task structural damping, I have a set of SOFiSTiK variables that I need to configure first. So I have a system made out of reinforced concrete. From the literature, what I can expect in terms of structural damping from a reinforced concrete bridge is a damping ratio of 1 to 1.5%. I am using an average of that in the form of 1.3%. I also have to define a relevant frequency range. I'm not expecting to go down below my natural frequency number 1, which is rather close to a human walking. And I'm not going to go beyond my natural frequency number 2, which is a higher boundary of what we can expect from a human running. After that, I'm using a simple mathematical transformation to use those relevant frequency ranges in order to determine mass proportional damping factor and stiffness proportional damping factor. You can refer to this formula in the Dynam manual 315, and I'm saving those 2 damping factors as a rad A and rad B variables to be used down the line in a time history analysis. It is worth mentioning here that the transformation presented is based on external knowledge. So mass proportional and stiffness proportional damping factors are what is required for a time history analysis. And that's the input that it's up to the engineer to assemble correctly. Alright, we are ready to start defining the forcing functions and start analyzing our bridge's response to dynamic loading. So in the task forcing functions, we have 5 load cases already defined, with each one of them introducing something new. Let's start with load case number 20, which represents just a sign-based generic periodic function. 2 components are needed here. Component number 1 is a defined static load, either nodal or beam or area loading, and component number 2 is a time domain function. The way this works is software defines function value at any given point in time and multiplies the values of static loading at this time step. SOFiSTiK offers a myriad of options to define your function properly. We will start with the basic 2, and that is a function's period and function's amplitude. So I have a period of 1 and the amplitude of plus minus half. Let's execute the code and let's have a look in the task report. And so SOFiSTiK always tries to draw a plot of the function that we have defined. And in our case, for load case number 20, we have our sine-based function with a period of 1 and the amplitude of half. What it means in practice is that the static nodal load of 10 kilonewtons that we have defined earlier will be multiplied by the resulting function value for every time step. And so for a time step 0, where the resulting functional value is 0, our effective loading will be also 0. At the time step of 0.25, the 10 kilonewtons will be multiplied by 0.5, yielding 5 kilonewtons, and so on and so on. Let's assume now we're interested in obtaining a sine-based function that fluctuates between 0 and 1 and that has a frequency matching the natural frequency of the bridge. Let us move over to SSD and let us consider load case 30 that represents just that. So the new functionality here in comparison to the previous load case is first and foremost adjusting the period of the function to match the natural frequency, the first natural frequency of the bridge. And second modification is adding func add and or func mult commands. These two commands allow to add a second function, in our case a linear function with a constant value of half over the period between 0 to 5 seconds, and the command add summarizes the resultant value in every time step of function 2 and function 1, and func mult multiplies these two values. Let's jump over to the task report now and let's see the resulting function. And so for the load case number 30, we have a plot representing the increased frequency of the forcing function, matching 1.83 Hertz being the first natural frequency of the bridge. And we see a second plot for the second function, which is effectively a constant of 0.5. SOFiSTiK will not draw a combined plot of these two functions together. It will draw the plots separately. In the analysis, however, it will summarize the two values for every given time step. The result is a periodic function with the frequency matching the first natural frequency of the bridge and the amplitude of 0 and 1. A simple sine-based function like this does not represent a pedestrian movement, however, so let's jump over to SSD and have a look how we can achieve a more complex function represented by a Fourier series. Let us consider a load case number 40 now, and what this load case is meant to represent is a group of people with a weight of every person set to 800 newtons, jumping in step in the frequency matching the first natural frequency of the bridge in the time span of 5 seconds. You will notice that a new function setting as jump has appeared. SOFiSTiK has several human body motion functions already built in for walking, running, and jumping. These functions are ready to use and can be invoked with a specific command. You can always refer to SOFiLoad manual for more details. In our case, and since we're only considering stationary loading in example number 1, we're going to use a pre-coded function for jumping with associated Fourier coefficients and phase angles as developed by Seiler and Hüttner. Let's jump over to the task report and let's consider the resulting function. And so for load case number 40, we have a plot representing the periodic function for jumping. The shape of the plot and the resulting values are somewhat different than what we would expect from walking or running, and that is tied to the fact that in a jumping motion there are prolonged periods of time where feet have no contact with the bridge's deck, and that is followed by an impact of landing and jumping up again. In any case, we have a frequency matching the first natural frequency of the bridge, and we have a start at 0 seconds and end of the function at 5 seconds. What we can do right now is we can try to run our first time history analysis starting at 0 seconds and running for 10 seconds, the first 5 of which the bridge will be affected by the forcing function representing jumping. We will be able to check two things through that small analysis. First thing is the positive action of the forcing function acting on the bridge's deck, and that will be the first 5 seconds of interest. And in the latter 5 seconds, so in the time span from 5 to 10 seconds, we should see the vertical deformation of any selected node diminishing with every cycle, and that should give us insights into structural damping defined earlier. So we have our periodic function ready. The amplitude of the function ranges from 0 to 4. Let's confirm our static load. We can do that in a graphic module by reviewing loading associated with a load case number 40, and we can see a group of 12 people with every person represented by a nodal load equaling 800 newtons, and these 800 newtons will be the values multiplied over time by a function value at any given time step. And with that, our forcing function is ready, and we can step back to SSD into the ASA module to configure and run our time history analysis. There are several aspects of the analysis that we have to configure and that require our attention. We have to configure the type of the analysis. In our case, a linear analysis is absolutely fine, as we do not expect any nonlinearities at this stage. We have to configure the primary load case that will serve as a basis of the shape, deformed shape under dead load and superimposed dead load in our case. We have to define the time history analysis itself, and the most important settings here are the number of steps and time step size dt. Selecting an appropriate time step size is absolutely critical, and a balance needs to be struck here. Setting the time step as too large will not provide enough fidelity into structural response under dynamic loading. On the other hand, setting the time step as too small will unnecessarily overload the SOFiSTiK with a sheer amount of calculations that do not bring that much into the table. Next up, we have a couple of settings that allow for a degree of control over the analytical method, load case numbering, and the results extent that is to be saved. We need to apply an appropriate damping parameters to the superstructure groups. We need to import nodal masses representing superimposed dead loading, and we need to invoke our forcing function, in our case that is number 40. Please keep in mind that we are trying to run the analysis for 10 seconds. Therefore, we have set the number of time steps for 500 with a time step equaling 0.02 seconds. So 500 times 0.02 equals 10 seconds exactly. For more information regarding the configuration of ASA and specific settings presented here, please refer to the ASA manual. The task has been already executed, so let's go over to Animator and review the results. So for every time step, a load case containing the results has appeared, ranging from 0.02 all the way to the required 10 seconds. And for the first 5 seconds, we're expecting the forcing function to act, and for the remaining 5 seconds, we're expecting the system to settle back into the original state. So let's review. We can freeze the image, we can set the constant scale, and we can scroll through the time steps to see how the structure behaves in time. And right around 5 seconds mark, we see the maximum deformation and the system slowly settling, where we can observe the effects of damping acting on it. The structure's behavior over time looks good in the animator, but let's try to draw a plot of vertical deformation of one selected node, preferably in the midspan, over time, and let's confirm what we see in the animator. Let's select one node. In order to do so, we can select one quad in the middle, and let's say we will investigate a node number 221. We can go to results and create a tabulated vertical deformation of a selected node over time. So we need results, nodes, nodal displacement in global z direction. We need a node number 221 specifically, and we need to select only dynamic load cases from 0 to 10 seconds. Check selected. And we have a list of our values that we can now represent in the form of a diagram. So for an x-axis, we will have load case. For vertical axis, we will have nodal displacement. And I want to draw a plot for a specific node, node number 221. And SOFiSTiK formulates our data in the form of a plot that effectively is a vertical deformation of our bridge's midspan over time. Right around the middle, so 1255 load case mark, we clearly see the maximum vertical deformation is being reached, and the system slowly settles back into the zero state through the means of structural dumping. We just need to confirm the load case 1255 is around the 5-second mark, and it is, which confirms the correctness of our analysis. We can also check how our loading condition develops over time. In order to do so, we can open graphic, and we can review the loading for every dynamic time step. We see two types of loading. We see uniformly distributed 6.2 kilonewtons per square meter. This loading represents dead load and superimposed dead load, which is present in every time step. And we see nodal load that represents a group of jumping people. And this is the loading that we associated with the forcing function. And we expect it to fluctuate between 0 and 0.8 times 4 equals 3.2 kilonewtons. So we start off with a time step 0.02, so we already see a value present. And we observe the value to increase, reach 3.17, and drop down again. We have not reached 3.2 kilonewtons because of the reduced time step and the fidelity it offers. If we would increase the number of time steps, we would capture the exact peak of the forcing function. This is not crucial in any case, so let's move on. We see the loading dropping down to 0. We see a short period of no loading between the impacts, and we observe loading picking up again exactly as the forcing function describes. The graphic module is also an excellent tool if we wish to review the envelopes of crucial results. In order to do so, we have to change the displayed results, go over to results, nodes, and let's say acceleration in the global z direction is of interest for us. If we zoom out, we can review the acceleration in every node for every time step, or we can scroll all the way down to envelopes of minimum and maximum results stored from every load case. Let's go back to SSD now and let's consider the next forcing function. We have reviewed and applied a forcing function based on a Fourier series representing jumping as developed by Zajlan and Hüttner that was already built into SOFiSTiK. We've already mentioned earlier that SOFiSTiK offers a range of useful forcing functions already built in. It also allows for a configuration of your own functions using TedD. There might be cases, however, where it is more practical to define your forcing function externally, for instance an Excel spreadsheet, and import it back into SOFiSTiK. We will look at how to achieve just that in load case number 50, where we will try to define a forcing function describing a jumping of the same small crowd as in load case number 40, but using different Fourier coefficients and phase angles as developed by Bachmann. In order to do so, I've prepared a small Excel spreadsheet that describes the Fourier series with the associated Bachmann coefficients as described by the external literature. I've already assembled the base values and coefficients required to calculate the forcing function over time with a time step t remaining the only variable. Please note that weight of a single pedestrian as well as the forcing function frequency are defined at this stage also. I've selected a natural frequency of the jumping motion to equal the first natural frequency of the bridge, same as it was with the previous example. The only thing remaining to do is to select an appropriate time step and calculate the values. We will use these time marks and resulting values as data pairs to assemble the function in SOFiSTiK. Therefore, the selected time step has to be small enough to provide enough fidelity into the function over time. I have selected 0.02 seconds as it matches the time step I'm planning to use in the analysis, and it should provide me with good enough accuracy. Let's calculate the function for a time span of 5 seconds now. We are at 2.18 seconds mark. 5.14. Let's remove the unnecessary part. Great. Let's scroll all the way to the top and you can see 3 columns. I've added a third column as the forcing function representing jumping does not contain any negative values, therefore a small transformation. Let's hide the unnecessary column and let's create a Excel plot to confirm that the values are what I'm expecting to have. Let's go to data, insert, recommended charts, and this is the plot that I'm looking for. Bachmann jumping function differs slightly from Seiler-Hüttner function. That's okay. Now onto the question on how to represent or copy this function into SOFiSTiK. We've mentioned before that SOFiSTiK is capable of formulating a discrete polygonal function described by several data pairs. We will use this capacity now. First thing we need to do is to formulate the data pairs in a way that SOFiSTiK can recognize them. In order to do so, we have to add, let's say, headers in front of every row. So this is going to be T, this is going to be F. Let's add one more row and let's drag it down for the entire data. Great. This is now the data that we can copy, and let's make an intermediate step in Teddy for a second, because we need to swap the commas into dots, as dots are what CADIP language assumes. So let's use a replaced function, dot for a comma as replaced. Let's copy this data back into our SOFiLoad task in SSD, load case 50, node. Let's paste it. It is not recognized yet. We have to instruct SOFiSTiK that it's a function. And it has been recognized. Let's check the completeness of our function. Yes, all 5 seconds are here. Let's execute this code. And let's review the resulting function in the report. Load case 50. And our resulting jumping forcing function has been introduced into SOFiSTiK for further use. We have defined the function for the 5 seconds only. This means that the function will equal 0 beyond the 5-second mark. Let's repeat the exercise done with the load case 40, where we performed a time history analysis lasting 10 seconds, first seconds of which the bridge was loaded by the forcing function, but let's apply load case number 50 now. In order to do so, let's jump into SSD now, into the task analysis ASA, and let's swap our load case with load case number 50, and let's execute. I've already executed the analysis, therefore we can jump directly into the results. Let's confirm the results for a vertical deformation over time in the midspan of the bridge. and we can clearly see the bridge is resonating for the first 5 seconds, after which the bridge slowly settles back into the zero state, which confirms the correctness of our analysis. Let's repeat the same exercise with the last stationary loading model, which is the central loading model for the random pedestrian flows. I've also used an Excel spreadsheet to calculate data pairs with a 0.02 seconds increment and copied these over into SOFiSTiK already. As mentioned before, this loading model requires an appropriate adjustment to the model shape that is to be investigated. In our case, the first eigenmode is the one to investigate for the vertical loading. The static load is now an area loading applied to reflect that specific mode shape. As the model shape and thus the loading pattern vary, the loading has been applied as a free area loading. The pedestrian weight and density are already included into the forcing function, so the static loading magnitude is set to 1 or -1 depending on the required direction. Let's check the resulting load in graphic. And this is what we want to see, so let's move on. Let's recalculate our system for this load model then. Back into SSD, we have to make sure that a load case 60 is the one that we're gonna provide to ASA as a reference. Let's just confirm load case 60 spans 5 seconds, and it does. Let's move over to ASA. Let's switch over from 50 to 60 load case, and let's execute. That concludes the analysis. Let's open results. And we do see the structure resonating for the first 5 seconds and then settling down for the latter 5 seconds. If enough time was provided, the structure would settle back to zero. The deformation values calculated are somewhat extreme, but please keep in mind that we are not considering a realistic structure, but rather a training example that is meant to amplify the dynamic behavior. Let's use this opportunity to highlight the dangers of external loading acting with the frequency matching the natural frequency of the structure and thus causing resonance. These midspan deformation values have been caused by central loading model acting in tune with the structure's first harmonics, so 1.83 Hz. Let's try to change the loading frequency without changing the loading magnitude, and let's try to compare the results. In order to do so, let's copy load case number 60 and let's redevelop it with a different number for a different frequency. So copy and paste. Let's change this number to 61 and let's note a change in the frequency to 2.5 Hz. And let's add this small description to the original one for clarity. 1.83. And let's jump to Excel spreadsheet that is containing our function. And let's change the frequency to 2.5 Hz. The function has recalculated, or the data pairs have recalculated. Let's copy them over to SSD into the load case number 61. We keep in mind that we need to add a function and we need to change commas into dots. And that should be it. So let's try and overlay the vertical deformation over time of load case 60, so 1.83 Hz, and load case 61, so 2.5 Hz, so we can compare. We can use results and Excel spreadsheet to do so. I'm still displaying load case 60, so let's copy those results, right click, configured copy. Let's go to new sheet in Excel spreadsheet and let's paste my original values here. Let's go back to SSD. Let's execute. And let's recalculate our model for a load case 61. Right off the bat, I can see that the vertical deformation plot over time is wildly different. So let's overlay them. Again, configured copy. I actually need just the values. And let's create a chart. Through insert, recommended charts, and we have our data. So the orange plot summarizes the vertical deformation of the bridge midspan for the loading acting with the frequency matching the first natural frequency of the bridge, whereas the gray plot summarizes the vertical deformation under the same loading but with a different frequency, which is a great way to display the dangers of resonance. And with that we conclude the first example. Now let's jump over to the slide summarizing example number 2 with moving loads. This example builds on the previous one and introduces the forcing function movement over time. As most model parameters remain exactly the same as before, we will focus on new functionality only. The main changes involve extending the model's geometry by adding a moving spring and possibly a pedestrian marker and mass, reassigning the forcing function acting node to that of the moving spring or a pedestrian mass center, and developing the ASA analysis to incorporate the lawn command that allows to translate the moving spring by a given vector at every time step. Let's jump over to the SSD now and let's investigate example number 2 in more depth. And so in the material and system task of example number 2, a new material and a new cross-section both for the pedestrian marker appear. A new variable dz appear that is to be used down the line. And if we scroll all the way down, we will notice a new group 99 that contains a spring, a beam, and a node that can be assigned a nodal mass marked as pedestrian markers. Lastly, a short command in ASA is required called MOS. The MOS command is meant to designate the previously created spring 99003, as visible here, as a moving spring, and to indicate the group geometry that the moving spring can search the new nodes to connect to from. We also use the previously defined variable dz to indicate the spring's initial length. Let's execute the code and let's review the result. So the overall geometry of the bridge system itself remains unchanged in comparison to the example number 1. We have introduced, however, a pedestrian marker consisting of a moving spring, 2 nodes, and a beam. Nodes 10,001, 10,002, and a beam 99099. So the bare minimum for the analysis is the presence of the node with the associated spring. Forcing functions are applied to the node, and the whole package can be moved with every time step by a given vector. After every shift, the spring will locate the closest node from the target geometry group and will link with it. Adding the beam and the upper node is an optional expansion of the concept. The beam itself can serve as a visual aid to indicate the position of the pedestrian at any given moment. The upper node, if positioned in the human body mass center, can have a nodal mass assigned to it, which allows for even a higher degree of precision in the analysis. When it comes to dead load and superimposed dead loading, no major changes are done in comparison to the previous example, other than switching the pedestrian marker group off. The same goes for the model analysis, and the structural damping remains unchanged as the structural system itself is the same as it was before. Forcing functions are structured in exactly the same way as before also. The only difference is that now the loading is applied to the node on a moving spring. In this example, you will find 4 functions, 2 to describe walking and 2 to describe running. It is possible to use both Zeiler and Bachmann coefficients that are predefined by configuring your SOFiLoad inputs accordingly. please refer to the SOFiLoad manual chapter on functions for pedestrians to learn more. Please note that predefined functions assume a pedestrian weight of 1 kN, so if you wish to adjust it to other value, you can do so by adjusting your static nodal load. You can also alter the number of pedestrians at any given time. If you opt to define your function externally, then the pedestrian weight is usually included into the formula, and static load in SOFiSTiK becomes a unitary load only. For a longer analysis that is meant to cover the entire length of the bridge, for instance, it is a good practice also to save your function that appears in a separate file to keep the SOFiLoad task organized and workable. The analysis task itself builds on the previous example with further developments to allow for a forcing load movement. A basis for the task is a loop function with a number of loops equal to the number of time steps we choose to perform. We can determine the number of time steps by considering the bridge length, pedestrian speed, and the time increments between the time steps. For every time step, a current position of the loading is calculated and applied via the laun command. Please note that if the loading is meant to move in a nonlinear fashion, it is possible to stitch multiple loops or even separate ASC tasks together, as long as the continuity is preserved by indicating an appropriate primary load case. A completely free movement of the loading can be achieved by combining SOFiSTiK with the power of parametric environment like Grasshopper, where a translation vector for every time step, along with the ASC input, can be generated. We perform a straight line movement in this example only, but the principle and code structure remains always the same. So for the analytical example, let's try to simulate a group of runners running the entire length of our bridge. I have already defined task-specific variables like the bridge length or the pedestrian speed to make sure the time history analysis will cover the entire length of the bridge. Let's use load case number 40 to run our analysis. Let's just quickly confirm in the forcing function task load case number 40. In this load case, we have a forcing function that's been already predefined by SOFiSTiK based on the coefficients by Zeile and Hübner. We adjust it to the bridge second harmonic. We adjust a pedestrian weight to 0.8 kilonewtons, and we have 3 pedestrians running. Since I know 3 pedestrians running on the concrete slab will not have that much vertical deformation effect on it in comparison to dead load, let's change it for the purpose of this exercise to 10 people running in step. And with that ready, let's go over to ASC task and let's run the time history analysis. And the analysis is done with 761 time steps calculated in just under 5 minutes. Let's jump over to the animator and let's review the results. And that is a successful analysis for our goals. You can review all the results as before in the graphic module and in the results module. Now let's move to the example number 3 and its brief summary. The last example differs slightly from the previous two. The bridge deck is now curved, and since we're planning to use Dyna module instead of ASC, we need to generate a nodal sequence that will inform SOFiSTiK about the planned loading trajectory. We can do that by creating a structural line, as SOFiSTiK always creates a nodal sequence for any structural line defined in the SOFiMSHC. We will use SOFiPlus preprocessor to create our model. Also, if the time history analysis is to be performed on a shape under self-weight, it is required to update the system's geometry with the relevant load combination. The next difference is the way forcing functions are being defined. Due to Dyna characteristics, it is necessary to represent the pedestrian in the form of a custom load train that is then to be multiplied by the periodic function. Dyna will be moving this load train along the preselected nodal sequence with a specified velocity. And lastly, the way the Dyna task is configured differs somewhat from the ASC module, although the principles remain the same. Let's jump into the SSD now and let's investigate the model further. As mentioned, we will be using SOFiPlus to generate our model. Let's jump over to SOFiPlus right now. What we have here is a similar structure with roughly the same span length, but with an added curvature and a structural line following the bridge axis. The structural line does not have a cross-section or any other structural properties assigned. It has been created as a reference for the loading path in the time history analysis. Let's export it now. And that's our meshed system. Let's have a look at dead loading and superimposed dead loading next. The loading conditions remain unchanged in comparison to the previous two examples, with one difference, and that is the last ASC task that allows to update the geometry system of a selected load case. Let's leave it switched off for now and let's execute. And let's move over to the model analysis. We do have to remember about keeping the load case number 10 as additional mass. Let's execute. And let's review the results. So the natural frequencies of the structure have obviously changed due to changes in the geometry itself. But the first and second harmonic of our structure are still the relevant ones for the vertical loading. So let's treat natural frequency number 1 and 2 as our boundary frequencies for structural damping calculation. When it comes to forcing functions for application to be used with Dyna, two major changes have to be done. First of all, we have to define our static load in the form of a load train. In our case, I have specified a point load, 0.8 kilonewton times 3, so approximating 3 pedestrians. And we always have to use func_mult function, as the time domain function have to be multiplied by the load train value at any given time step. Moving on to the analysis itself, the way Dyna analysis is configured is very similar to ASC analysis in that we have to define our load velocity, we have to define our time increment, and definitely we have to import the superimposed dead load masses, and we have to assign structural damping to the appropriate superstructure grouping. And from there, we provide the number of time steps to be calculated together with the previously defined time increment, load case number, and the loading trajectory together with its velocity. Please note that the number 99 refers to the number of the structural line in SOFiPlus that we have created earlier. Let's confirm. Confirmed. Let's go back to SSD. Dyna offers a lot of configurability as well, like the type of the numerical analysis to be used, for instance, or how extensive the results saved for each time step should be. Please refer to the Dyna manual to learn more. One last thing for us to do before we can run the analysis in Dyna is to update the system coordinates to reflect the deformed shape under deadload and superimposed dead loading. In order to do so, let's go back to deadload and superimposed deadload task, and let's run this little code that will update our original geometry with a deformed shape stored for load case 1001. Let's execute. Let's go back to Dyna and let's execute also. With the analysis complete, let's move over to graphic and let's review our static load for every time step to confirm the correctness of the loading applied. So because I have opted to store loading for every time step, I now have a full visibility of where my loading is at any given moment and what magnitude is it. So let's just confirm a couple of steps. We can clearly see the time domain function working, and we can clearly see the loading shifting along the pre-specified nodal sequence. Let's just confirm how many time steps we have in total. I have asked Dyna to perform 1,000 time steps. We will see less static loading saved than that because we will run out of the nodal sequence length eventually. So under the number 702, we're already at the end of the bridge, and the last time step with any loading on it is 804. From that point on, the bridge will just settle by the means of structural dumping. Let's go over to the SSD now and let's review the deformation over time. Alright, the deformation recorded over time indicates a successful analysis. Again, you can access detailed results in the graphic module and the results module. And that concludes the example number 3 and our webinar. I would like to thank you for your attention and wish you much success in your design work. If you have any questions or queries, please make sure to email us directly, engage us on our social media, or reach out to one of our local partners or representatives. Thank you.